Hi there, this is Richard Walker from Lucidate. Welcome to this series of 2 videos on Exploratory Data Analysis, EDA. We need to train and test our AI models. AI solutions require large data sets during training so that they can effectively generalize when running on live data. It's critical that training data is representative of the data that the model will see when it's put into production. It's also critical that the training data is clean. The old GIGO adage holds as true here as anywhere else. Garbage in, garbage out. For everything to work downstream, our upstream data hygiene must be clinical. In these videos, we'll describe some simple best practices that can be followed for pretty much any AI or machine learning system you're developing. Big or small, complex or simple, real-time or analytical. Following these simple principles will give you much better outcomes. The purpose of EDA is really twofold. Firstly, to help us cleanse the data. We want to identify missing or erroneous data points and develop a strategy for dealing with them. Secondly, to start to identify patterns and relationships in the data. This has 2 benefits of its own. Firstly, exploratory pattern shapes and relationships will help us develop better strategies when we build our AI and machine learning models. Secondly, patterns that we spot here will help us dealing with missing values or incomplete data. It will give us guidelines to fill in missing data rather than simply discarding an incomplete record. AI has been widely and successfully used in financial services to support credit officers deciding on whether to approve loans. It's also been very useful in predicting customer churn. To reflect this, we'll be using a couple of relevant data sets that look at loan default prediction and credit card churn. Both these data sets are freely available on the internet at the addresses shown on your screen. There's also a link in the description. Let's start with the loan default dataset. We can drag the file into a raw canvas to begin our EDA. The first thing to do is verify with the correct data and take a look at some of the summary statistics. The file widget gives us the number of rows, the number of features, and whether those features are numeric or categorical codes. It's also identified the target value, the value we want our AI to predict. In this case, it's a flag of whether the loan was repaid or defaulted. We can view the data as a sortable table. We'll use this data table widget a lot as we build a pipeline for analyzing and cleaning our data. We can also see some summary feature statistics. This gives us a great place to start when looking for missing values and patterns. Here we see the mean, median, min and max values, the dispersion, which is the standard deviation for numeric data, and an entropy measure for categorical information. We've a count of the missing values per feature. In this dataset, there are 3 features with missing values: the debt to income ratio, the home ownership category, and the 90 days of bad rating flag. The first 2 don't have that many missing values. We can perhaps devise a strategy for these later, but with nearly every record missing in the 90-day bad rating flag, this particular feature is more troublesome. The distribution column also gives us some great early insights into some of the patterns. It shows a frequency histogram of each feature. By default, it's segmented by our target value, repaid or defaulted loans. So we get to see any variation in the distribution. We can easily remove this segmentation if we like to simply see the distribution of this feature, or choose to segment the distribution by another variable, such as credit rating. We'll take a close-up view of feature distributions a little later. At this juncture, and with this information, we can start to make some decisions. Firstly, we can see the ID column. This is an account number and it's unlikely to have any influence. Therefore, we can delete it. Indeed, we should delete it. It's only likely to make the model worse at generalizing. Then we have the 90 days bad rating feature. This is so sparsely populated that we'll get no meaningful signal from it. We'll drop this along with the ID column. We can delete both features using a select columns widget. We can also see that there's a coding error in the term feature. Some records are classified as 36 months with a capital M and some with a lowercase m. We'll fix this. To deal with the upper and lowercase m in our term variable, we can use a widget to clean up this encoding error. So we've taken our first small steps to clean up the data. When dealing with our information, we'll use different strategies for numeric and categorical data. Numeric can be either continuous, usually floating point, or discrete, just sticking to integer values. This includes a lot of binary yes, no, or 0 and 1 data. We also have categorical data. These are coded values, often represented as text. We'll clearly need to convert any text codes to numeric data in order to feed our models. The categorical data comes in two forms. Nominal, where there's no particular order, rank, or hierarchy in the data. Examples are marital status or city codes. Alternatively, data can be ordinal. Credit score is a great example, where there is an explicit order to the data. We'll look at categorical data in the next video, and in the remainder of this, focus on numeric data. With numeric, we'll need a strategy to deal with missing values and outliers. Outliers are a tricky topic. On one hand, outliers can be legitimate, and you'd like to have sufficient data coverage in training so your model can handle the inevitable outliers when they occur in production. On the other hand, you do want your model to generalize well. Outliers can really screw this up. It's a kind of battle between theory and practice. Theory might argue that you keep outliers in. Practice says you throw them out. Trust me, practice wins. Nearly always. The good news clearly is you can split your pipeline right here and train your model with outliers in and outliers out. Then pick the model that generalizes best. Nearly every time it will be the one where you have thrown out the divergent data. So enough about the why on outliers, let's get to the what and the how. Box plots and histograms are ideal for outlier analysis. For brevity, we'll here just illustrate analysis on a couple of features to get the key points across, but clearly you need to follow these steps for all of your features. The histogram shows us the distribution of our data split up into discrete bins. At this stage, you can gain some great insights into some relationships between features by splitting histograms. Here you can see the debt to income ratio split by our target variable. There's some evident and frankly expected skew, with lower debt to income for non-defaulters than defaulters. But other patterns emerge too. Rather than looking at debt to income by default, another split might be by credit rating. Again, we can see a similar skew between the highest ratings and the worst ratings. Changing the histogram bin sizes helps clarify this. The box plot shows us the locality, spread, and skewness of data using quartiles. For continuous numerical data, the box is drawn on a number line. The leftmost part of the box is the first quartile, and the right of the box is the third quartile. The median is marked as a line within the box. Whiskers can then be added, with the left whisker being the min and the right whisker being the max. The box plot helps us clearly identify outliers. Best practice, indeed standard practice in machine learning, is to reject outliers using the IQR method. To do this, we first identify our interquartile range, or IQR. This is the difference between the 75th percentile value and the 25th percentile. We then multiply this IQR by 1.5 and subtract this product from our lower quartile, and at the same time add it to our upper quartile. This sets up two fences. Any data outside these fences is considered an outlier and will be rejected. So let's take a look at some of our continuous data using these box plots and histograms. Firstly, let's look at our annual income box plot. Here we can see a very, very long tail in the upper quartile of the data. This extends well beyond our upper fence. We can apply an IQR filter to the data. This will reject 926 outlier records. The histogram on the right shows the annual income feature after we applied the IQR method to it. We've lost the long tail of income in the upper quartile of the data. The histogram on the left shows the annual income distribution before the application of the IQR filter. This contains all the outliers. While these outliers are legitimate, their inclusion makes our model worse at generalizing and selecting the loan applicants that actually do default. If we look at debt to income ratio, we can see that the whole distribution fits within our upper and lower fences defined by our interquartile range. I won't go through every example in this video, but this should be standard practice for numerical variables. If there are reasons for keeping outliers in, then by all means do, but make sure that you have a good reason. Next up is to analyse correlations in our data. Information here will help guide us later when we apply our AI models, and it may also help us now in dealing with missing data. We may be able to impute some missing values based on correlations with data that we do have. In this data set, our largest correlation is a weak negative one between annual income and debt to income ratio. Again, unsurprising, the more people earn, then the lower you would expect their debt relative to that earning to be. Other than this, the features are pretty uncorrelated. So this first video has covered the basics in exploratory data analysis. We've described why we need to perform EDA and introduced two data sets, customer churn and loan default. These are two areas in which AI has been particularly successfully deployed in financial markets. We've looked at tools to analyse our data, beginning with summary statistics to look at the distribution of each feature. We've also used the box plot or box and whiskers plot to help us study outliers, as well as remove potentially troublesome outliers with the IQR method. This is Richard Walker from Lucidate. Please join me in the next video when we will conclude this short series on exploratory data analysis. In that video, we will look at our other data set related to customer churn, and also we will explore, analyse and clean our categorical data.